Okay, AP Calc, welcome. Today we're going to be talking about some properties of definite integrals. Now I know we've been using the fundamental theorem of calculus. We're actually going to take a step back and take a little bit look at some of the properties of definite integrals. So in your notes, the title for this section is just going to be the properties of definite integrals. And remember that a definite integral is an integral that has a range on it, right? So you're evaluating an integral from a to b as opposed to an indefinite integral which has no range on it, right? So it's just the sigma sign with no a or b attached with it, in which case your answer needs to have the constant, whereas when you're evaluating it from a to b, the constant goes away. Basically, so our objective today, by the end of this lecture, this short lecture, I want you to be able to evaluate a definite integral using the properties of definite integrals. So you know how to evaluate definite integrals. I'm just going to put def integrals, or def int. But now I'm going to give you some properties of definite integrals so that you can manipulate. Basically, these are just different ways that integrals can be written. And once you know these properties, you can manipulate them, and usually it simplifies your problems. It makes it way, way easier. You can solve a wider variety of problems. So you're evaluating definite integrals using properties of definite integrals. Okay, now some of the properties that I'm going to give you, some of them are going to be really simple and obvious. I'm going to try to explain them. Each one I'm going to try to just give you a property and then give you a quick example, give you a property, give you a quick example. Okay, so the first one we're going to look at, so I'm going to say prop 1. Okay, if it says if f is defined at x is equal to a, then if you're taking a definite integral of any function, it could be any function, so f of x dx, if you're going it from, instead of from a to b, if you're going from a to a, a little weird, then this is going to be equal to 0. Now this 100% makes sense if you think about just sort of your general function, right? So I've got some general function right here, f of x. Normally, I'm looking at a function from a to b like this, right? And then we're calculating the area in this region. But imagine I take this b region and I start moving it over further and further and further, right? So my area is going to get smaller and smaller and smaller. So if I think about my b region being up here, it's getting smaller, smaller, smaller. So my area is getting smaller, smaller, smaller. Eventually, like if I push it all the way to a, so if I'm just looking, not even just like at a tiny sliver of a, but just at a, my integral is going to be equal to 0, right? Because I'm going to have 0 area. I'm squishing it so far down, it's becoming infinitely skinny. So basically, my area is going to be equal to 0. And you can actually prove this to yourself if you think about the fundamental theorem. So this is according to the fundamental theorem. So if you say f of a, normally it's f of b minus f of a, but if my a, my a are the same, or my two intervals are the same, then I just get f of a minus f of a. And of course, that's going to be equal to 0. Okay, so the quick example of this one, and any integral, it doesn't matter how crazy it looks out here. If it's from a to a, then the answer to the integral is going to be 0. So the example I've got for you here is, say you're taking the integral of sine of x dx from pi to pi. Now right away, all you need to do is just realize that, hey, the upper and the lower limits are the same, or the interval that I'm looking at is exactly 0. It has 0 width, so it's going to have 0 area. Okay, property 2, prop 2. Prop 2 says that if f is integrable, right? So crazy word, means if you can integrate f. If f can be integrated, over this interval on a to b, once again our generic interval, then this is true. So a to b right here, f of x dx is just going to be equal to the same thing if I just flip these limits, or if I flip these the ends of my interval. So from b to a, this one's going to be a negative. So it's going to be negative b to a f of x dx. So basically, if I swap these two numbers, then the equivalent thing is to say it's going to be a negative. And once again, you can prove this to yourself. So in this case, this one right here, using our fundamental theorem, so we could say f. This is basically saying f of a minus f of b. Right? That's what this one is equal to. Now this one right here is, I'm going to ignore the negative sign for just a second. This one is going to be f of b minus f of a. Now if this whole thing has a negative sign in front of it, right, then that negative sign gets distributed in, so then I have a negative b over here, and I have a positive f of a over there. So it makes sense. Property number 2. So how you're basically going to see this one is if your interval is backwards, right? If it doesn't make any sense, basically. So from 0 to 3, x plus 2 dx. This doesn't really make a whole lot of sense because 3 is a larger number, so the larger number usually goes on top. So you can just rewrite this and just say, okay, so this whole thing is just going to be equal to negative. And then I just flip these things. So it's going to be from 3 to 0 of x plus 2 dx. Now you guys can solve this, but might as well just in case you guys want a quick refresher. So negative, and then the x just becomes square bracket. So then I get x to the n plus 1, so it's going to be 1 plus 1 over n plus 1, 1 plus 1, plus, and then a constant, the derivative, or the integration of a constant is just going to be 2x, and that's going to be from 3 to 0. Remember to keep track of this negative sign here. That's the whole reason I'm doing this property. Okay, so same thing. So then I just get x squared divided by 2 plus 2x from 3 to 0. Just doing one step of simplification there, from 3 to 0. And then the next one, I can start plugging in my 3 and my 0, so negative sign out front. And I just end up with 3 squared divided by 2 plus 2 times 3. That one. And then the negative sign, because it's a negative sign, I'm going to go ahead and distribute it, so then it just becomes a plus, right? So normally it would be f of a minus f of b. In this case, it's f of b minus f of a. So then now I've got the 0 goes in, and both of these terms have a 0, so I just get 0 squared over 2 plus 2 times 0. So this term entirely goes to 0. 3 squared over 2 is 9 halves. So I just get negative 9 halves plus 6. And this is just going to be equal to negative 21 over 2, negative 21 halves. Okay, that's our second property. Now our third property it's called the additive interval property. Okay, a little bit different. It has a special name. So prop 3. This is the additive interval property. Now this one mostly makes sense if you think about what an integral is. Okay, so I'm going to start off by drawing our general function here with x, y, and here we've got f of x. This is y. Okay, so once again, if I'm looking at an interval from b to a, and if I'm integrating this from a to b, f of x dx. Okay, once again, what I'm looking for is the area between the curve and the x-axis. So I'm going to shade that in with yellow. Hopefully you guys can see that. Shade it in with yellow. So now when I do that, okay, say I took the same interval and I chopped it up. So I took some point in here. It doesn't have to be the midpoint. I'll put it over here. And I chopped it up and I said, okay, so I've got this point over here, C. Well, it's the same function. So this yellow area is going to be exactly equal to the area between A and C and the area between C and B. So the area between A and B is going to be the area here plus the area here. So it kind of makes sense. Okay, that's what this additive interval property says. And so basically, let me give you the math definition, and then we'll jump into an example. From B to A, f of x dx is going to be equal to, right? So that's a whole interval. From A to C, f of x dx. And so, for example, that one, that interval is going to be right here. I'll put it in orange. That's just that interval right there. Now, of course, it's a yellow shaded region of just that orange area, plus from C to B, f of x dx. And I'll put this interval in pink, and that's just this interval between C and B. So that's all it's saying. Nice visual going on there. This is the additive interval property. Let me go with example C, and we'll go from here. So say I've got a function like an absolute value function. That's what this is most commonly used for. And so if you think about an absolute value function, right? So say just if I'm plotting f of x is equal to the absolute value of x. Now, stretching your brains back or going forward, you can see that, or you can remember that the absolute value of x, the function that's associated with this, just looks like this, right? So it's going to be a positive x in this direction, but in the negative direction, it's a linear line, right? So it's a line of slope 1 that crosses the origin. But then it's going to be all normal in the positive region. But in the negative region, it's not going to continue to go down. It's going to come back up and go like this, right? So this is the plot of f of x is equal to the absolute value of x. So here you can see we don't have a continuous function, because we have the sharp turn, or we have a continuous function, but we don't have a differentiable function, because we have the sharp turn right here at x is equal to 0. And so here I can use the additive interval property. And so if I say, okay, from 1 to negative 1, absolute value of x dx, now I need to break it up. Okay, so this is going to be equal to 0 to negative 1, negative x dx. Okay, so that now I'm just looking at, say, this is my value of negative 1, this is my value of positive 1, okay? So I'm looking for this area right here. I'll shade it in with orange. So that guy and that guy. So basically I'm saying, okay, so the area under the curve, between the curve and the x-axis of this orange region right here, is going to be the area of this chunk right here plus the area of this chunk right here. So I can't really integrate the entire thing because the integral of an absolute value gets kind of funky. But I can say, okay, well, the function of this line right here, or the function of this line right here is negative x. So it's a negative slope of 1, and it crosses a 0, 0. So that's this function right here, from negative 1 to 0. And I can just add it to this one. Now this one's easy. Okay, it just goes from 0 to 1, and it's just x dx. Now if I do the same thing, or if I start doing my integration here, that was sort of the tricky step to make that jump right there. And so if you're still with me, keep with me. We're almost done. So if we've got negative x dx right here, this one just becomes, hopefully you guys can do these integrals a little bit quicker now. So we get negative x squared over 2, okay, and we're looking at that one from 0 to negative 1, plus this one just becomes x squared divided by 2, right? So that's just x of n plus 1 over n plus 1 from 1 to 0. Now looking at this, when I plug 0 in here, so plugging 0 in, I get 0 minus this one, I get negative x squared, or in this case I'm plugging in 1, so I get 1 squared divided by 2 there, plus, now I'm just plugging in the values here. Once again, hopefully you guys can do this a little bit quicker. So I plug in 1 squared divided by 2 minus my lower limit, which is going to be 0 squared divided by 2, which is just going to be 0. So taking a look at this stuff here, so 1 squared divided by 2, that's just going to be 1/2. And then I've got a negative and a negative, which is going to be 1/2. Okay, so 0 plus 1/2 is just 1/2. So what is this right here? Just this section right here, just this 1/2 right here, is the area of this right here. Kind of cool. Now if I do the same thing here, I get 1 squared is just 1, 1 over 2 is just 1/2, minus 0, so this is just going to be 1/2 as well. So sure enough, this area is 1/2, this area is 1/2. That makes sense because both of them is pretty much the exact same area. Okay, this is just going to be equal to 1. So my total answer is going to be 1 unit squared. And check this out, okay? So what we just did with this linear thing, this is just sort of a side note. I want you guys to take a look at it though. But what are we looking at here? This orange region, just this orange region on the right, this is a triangle. This is the area of a triangle is what we're trying to find. And the area of a triangle that we know is area is going to be 1/2 base times height. Now my base is 1, and my height in this case, I try to figure out what my y value is here. So if I plug in 1 here, my y value, if I plug in 1 here, my y value is going to be 1. Okay, so sure enough, this is going to be 1 right there. So if I use the area of the triangle that I know, I get 1/2 of 1 times 1. Okay, which is just going to be equal to 1/2. Now if I integrate this same function over 1, so from 1 to 0 of x, that was this portion right here that's tied with this, I ended up with the exact same answer, 1/2. So sure enough, integration pops up when you're actually looking at the value or the area of regions, geometric figures that you guys already know. So you plot them on an xy coordinate plane, you integrate them, you integrate the function, and you end up with the actual true value of what that area is going to be. Or in this case, you can derive what the base and the height, or what the area of a triangle is using calculus. Kind of cool. Awesome, guys. I'm going to check out for now. I'll catch you guys next time.